Hey everybody, and welcome back. This is how to simplify rational expressions. So hopefully you were able to watch the intro to rational functions video, which preceded this one. So now we're going to start messing around with these rational guys. And the first thing we're going to do, which is kind of similar to what we did when we first learned like fractions, constant over a constant, was reducing, right? Remember how to reduce a fraction? That's all we're doing here. We're just taking all these guys that you see around the screen and we're just reducing them, okay? So don't think that this is any more complicated than what we learned in like maybe elementary school, how to reduce a fraction. It's the same thing. We're just throwing some letters in there with it, okay? But the concept is all the same. So let's see what I mean by that. So first, why do we simplify? Why do we reduce fractions? So if you thought back to like elementary school and be like, why did I reduce all those fractions? Well, simplifying is like cleaning it up. So it makes the rational expression easier to deal with, right? Instead of having like 9/81, wouldn't it be just a lot easier to deal with 1/9, right? Clean it up, make it simpler, make it easier to work with, make the numbers smaller. When doing long calculations, it's easier if you have simplified terms. So think about like really, really long physics equations or something, and you're dealing with a lot of numbers and it's getting really technical. Well, if those numbers are as simple as possible, right, you're going to make your life easier. It also helps with graph sketching. It helps us find holes, asymptotes, and domain restrictions as well when things are in their simplified forms. So that's why we simplify. So let's look at maybe how we simplify. So I'm going to do 4 examples. The first example I'm going to do is just a constant over a constant, and this is just to remind ourselves, hey, how do we reduce fractions in the first place? So this is going to take you back to elementary school, and then we're going to step it up a little bit, and we're going to do a linear, which is just an x to the first power, and then we're going to step it up even more. We're going to do a quadratic, and we're going to look at kind of x to the second power, and then we're going to step it up a lot for example 4, and we're just going to do, okay, what if I have a general polynomial over a general polynomial? Has anything changed? So let's start. So think all the way back when. How do I reduce 6 over 54? Well, when you guys did this in elementary school, you may have said, well, I need to look for things that divide 6 that also divide 54. Yes, what we are actually doing though is what I want you guys to think about here is I want you to not look at that color because it's too light. This color is much better. I want you to instead think about numbers as product of their prime factors. So 6 is what? 6 is 2 times 3. And I'm thinking about it this way now because this is going to be a lot more useful when we start introducing variables. Now what is 54? And this is where these factor trees come in handy. Well, 54 is 9 times 6, 6 is 2 times 3, and 9 is 3 times 3. So 54 is 3 times 3 times 2 times 3. Now when I have everything in its prime factorization, what I'm going to do is I'm going to go through in black and I'm going to knock out all of the common factors, right? Like 2 and 3. And now what do I have left? Well, 2 over 2 is 1, and 3 over 3 is 1, so there's going to be a 1 in my numerator. When you knock out all your factors, what you're left with is a 1. Remember, when you divide something by itself, it doesn't go away, it's just 1. And then I have 3 times 3 on the bottom, or 9. So 6 over 54 reduced to 1/9, right? And you think about the way that we used to do it, like, oh, well, I can divide by 6, divide by 6. What we're doing is we're actually taking out all the common factors here. So hang on to this. We're going to do this now. We're just going to throw in variables. So when we step it up a little bit, so now I got some variables in there. But I want to do the same thing. I want to break it up into its prime factors. Well, what do prime factors look like when I have variables in there? Well, think factor polynomials, right? We want to factor the whole thing. So if I factor this numerator, and this is why factoring is so important because it just shows up again and again and again and again and again. And if you could really nail down kind of like one skill when it comes to polynomials, factoring. So there's greatest common factor here, so I can pull out a 3 in my first term, and I'll be left with an x. I pull a 3 out of my second term, and I'll be left with a 3. Down here, 6 is 2 times 3, which we saw, so it'll be 2 times 3 times x. Now let's knock out some common factors. So I see a 3, I see a 3. Now here's something that gets confused a lot. There's an x down here and there's an x down here, but this x is not the factor. The x plus 3 is the factor. And you can't knock out a piece of the factor. You have to knock out the whole factor. So this x plus 3 can only eliminate with another x plus 3. I can't knock out an x and knock out an x because x isn't the factor in the numerator. X plus 3 is the factor. So I can only knock out whole factors, not pieces of factors. So that looks like the only stuff that I had. So now I'll rewrite it with what's left over. So we have x plus 3 in the numerator, and looks like 2x in the denominator. And now we're simplified. So factor numerator, factor denominator, knock out common factors. You got to knock out the whole factor, and then write what's left over. So that was a linear. Let's step it up a little bit, and let's do a quadratic. All right, let's kind of exercise our factoring muscles a little more here. X squared minus 81, that looks like a difference of squares to me. So that looks like x plus 9, x minus 9. All right, what about our denominator? Looks like we have a common factor, right? At minimum, I can see an x in both terms. And what else? I have 54 and I have a 6. 6 will go into both of these. So the common factor here would be 6x. So if I pull that out of my first term, I'd be left with x. If I pull 6x out of negative 54, I'll be left with minus 9. Now let's knock out some common factors. Hey, here's an x minus 9. Here's an x minus 9. Wonderful. So now what's left over? X plus 9 in the numerator and 6x in the denominator. Remember, I can't knock these two out because my factor is x plus 9. I can only knock out another x plus 9. I can't knock out a piece of a factor. I've got to knock out the whole thing. Okay? So this is as simplified as we're going to get. So now let's kick it up again. And now we got bigger powers at play here, but we're going to do the same thing. So as you notice, I've done the same thing every single time. I factor the numerator, I factor the denominator, and I knock out common factors. So let's play that game again. What do I got here? I have an x cubed in each term, so I'll take that out. And when I take out x cubed, I'll be left with x squared. Remember, subtract exponents. When I take an x cubed out of here, I'll be left with negative 81. Ooh, I got a difference of squares up here, so I'm going to have to factor that further. What do I have going on in the denominator? It looks like there's at least an x squared in each term, so I can pull that out. Pull an x squared out of there, I'll be x. Pull an x squared out of there, I'll be plus 9. Got to factor further, so I'm going to do that. X cubed, and then x squared minus 81 is a difference of squares, so that's x plus 9, and that's going to be x minus 9. Again, see how handy factoring knowledge comes in here? X squared and then x plus 9. Alright, let's do some knocking out now, because everything's as factored as it could be. X plus 9, x plus 9. What else? I got x to the third up here, and I got x squared down here, so I can knock out x squared. I can knock out x squared, which means I'll have one remaining x in the numerator, right? Because there was x up here, and there was just x down here, so 2 x's got knocked out, which means 1 will survive in the numerator. So then I am left with 1x survived the numerator, x minus 9, and in the denominator I knocked out everybody, so it's over 1. How do we write things when they're over 1? We just write them without a denominator. So that would be our simplified version there. So to recap our steps, so what did we do? Every single time we factored the numerator and we factored the denominator completely, every single time. And then we eliminated common factors in the numerator and the denominator, right? When we saw two matchy pairs, we said poof, and we knocked it out. But remember, we have to knock out the whole factor. You can't knock out x and x plus 9. You can't knock out those x's. You can only knock out the whole factor. So the factors got to match exactly. No knocking out pieces here. And then once you knock them all out, rewrite the simplified rational expression. And that's it. So thank you guys for watching this video all the way through. If you have any questions, please don't hesitate to ask. I hope that was helpful for simplifying rationals. There will be a follow-up video for this. We're going to add, subtract, we're going to multiply, we're going to divide, we're going to solve. So we're going to do all this stuff with rationals. So I'll see you guys in the next video.